We're recording now, and okay. And we've already gone over all of this, but it's important, really critically important for our understanding of the periodic table that we look at this, I think, again. So the periodic chart divides itself into several regions. The first two columns on the left are the s orbital group, and we've looked at that. That's the first row is going to have an NS1 outside the core. So all of them have one electron outside the core. They all lose that electron in reacting. And the only charge you're going to ever see for group 1 is +1. Group 2A is the second column in this S group, the first two columns. They're going to have an NS2 configuration, and they are going to always form ions of +2 charge. The right-hand side is a group of 6 columns. It's the P group. This is the region where the p orbitals are filling. If I go to this first one, that would be 3A. This is 1A, 2A. 3A is this column. Each one of those those atoms would likely form a +3 charge. Aluminum always does, because remember when we did nomenclature, aluminum was one of the atoms you did not need a Roman numeral. And then, so this would be a NS2, same N, P1. So it's the same principal quantum number for both S and P as you go across a column like this. And the first column here would be P1. The last column over here would be P6. That would be the noble gas column right here. So all of these are where the p orbitals are filling. And if you want to know how many electrons are in that outside p orbital, it just count over from here. 1, 2, 3, 4, if that's where you are in group 6, it would be there. Then the d orbital region is the middle region, and they are the B elements. 1B is way over here in copper and its family, the 9th element in the periodic chart across this row, and this one would be the 10th row, and that's group 2B, and then 3B is back over here. Now, you might wonder, well, why is it all so confusing like that? Well, because scandium in this point right here is 3 electrons away from a noble gas. It does form a +3 charge also. All of these elements in the whole group D group can form a +2, but they can form something else. That's why they need a Roman numeral in their name. And the +2 is common to all of them, but 3B also has a +3, and 4B has a +4, and so forth. When you get to the 8 elements, group 8, there's, well, there would be 9 if it's 3 rows in your periodic table column. It'd be 12. There's 3 elements across in any row that belong to this series of elements. They're group 8B. Sometimes they just call them group 8. Doesn't mean they have 8 electrons that they're going to give up. It's just something that has to do with the way they're arranged in the atom. But the charge number for group 8 is +2 or +3. And then the bottom row is the F group elements. The first row is the 4F and then 5F. Just like the first row here is 3D, but you're in row 4. It's 3D. And then the first row of p orbitals is 2p, because there is no such thing as a 1p orbital. You can't have L equal to N in that same row. So there is no such thing as a 1p. But row 2 can have p orbitals, and so forth as you're going up. Okay. Now, that's we've talked about families and things like this. Let's look here. This cartoon is addresses the size issue. You need to remember the size increases as you go toward the bottom. That makes the element more reactive as a metal. They tend to lose electrons. The thing that tends to surprise people is they get small going across a period. Even though the number of electrons increase, the volume that they're located in decreases. And as we mentioned in the original lecture, the reason for that is as you go, say you're in the p orbital region, you put one electron, the first one, let's say, maybe goes in the pz orbital. And the next one is going to go, let's say, in the px orbital. Well, those two orbitals are at right angles to each other and they have a node between them. So that means that an electron in the pz orbital does not experience the electron in the px orbital. So their electron-electron repulsion term doesn't increase like it does if they're in the same region, like in s orbitals and things like that. So what's going to happen is as you go from one element to the next, the nuclear charge goes up by one, but the electron repulsion charge does not. So that means that the electron's repulsion, which tends to make the atom bigger, is less than the electrostatic attraction for the nucleus when it picks up another charge. And so it pulls them both in closer. So you get the decrease in charge going across a period like that. Now, when we look at ionization potentials, there are several ionization potentials that are possible, equal to the number of electrons that particular atom has. Hydrogen only has one ionization potential. And by the way, that's that 2.18 times 10 to the negative 18 joules per photon that we got in the analysis of the energy level pattern of hydrogen. And that's the ionization potential for the atom. And all other atoms will have more than one electron, and they'll all have an ionization potential for each one. And so the first ionization potential takes the neutral atom to the +1, and that electron is released to something else. That's the ionization potential, is the energy it takes to remove that electron. Then that same atom, if it has a second electron, the +1 ion that's formed can also lose another electron and make a +2. And I think you can see, if I'm looking at this, as you go to higher and higher ionization potentials, the energy increases dramatically. And because this first electron, you're taking away from a neutral atom, but the second electron, you're taking away from something that was +1. So that's going to take a lot more energy to do that. So the ionization, multiple ionization potentials increase dramatically. Large atoms have low ionization potentials. Remember, the ionization potential is the energy to remove an electron from that outside layer. The further that outside layer is from the nucleus, the less energy it's going to take to get it. So large atoms on the periodic chart, and you remember the trend we just showed you a moment ago, have low ionization potentials, and then the others have high. Metals certainly have lower ionization potentials than nonmetals. And if you remember on the periodic table, I'll go back up here, right in here, there is a little zigzag stepped line on the periodic chart. And that line separates, that stair step separates the metals on this side from the nonmetals on this side. So if you're comparing ionization potentials, if something's metallic and you're comparing it to something that's non-metallic, you expect the metal ionization potential to be lower, and so forth. Okay. If you're looking at charged species, the cations are positively charged. So if you say, okay, if I'm comparing a cation to a neutral atom, Well, I'm expecting the cation's charge, ionization potential, to be larger because you're pulling an electron away from something that's positive. Likewise, if you've got an anion, it's got extra electrons already. That's the reason why it's negative. So it should be easier to remove electrons from anions than it should be from either neutrals or cations. Now, there's this right-hand column on the periodic chart, the noble gases. They have the highest ionization potential of all. Now, what do we know about them, and why does that make sense? We know that most of them won't react with anything. So if they don't react with anything, that means they're holding on to their electrons. It's an arrangement that is good, and they want to keep that. They don't want to lose electrons, for sure, and they don't want to gain electrons. So the energy to remove an electron from something that has a noble gas configuration is extremely high. And that's what you get also when you get either anions or cations formed from the element itself in its normal charge. Like, for example, if I take group 1, take 1 electron away, I got a noble gas. The first electron's easy to get away. The second one is extremely hard to get away because it's a noble gas. Or if I took beryllium, the second element, 2 electrons would come out rather easily, but the third one would be, because you'd have a beryllium plus 2 ion, and it would have a helium configuration. It would be very, very difficult to remove the electron. So that's why we think that atoms react to keep on releasing electrons from the metal or gaining them from the non-metal until they get to that noble gas configuration. And at that point, they're stable. So sodium is not going to release 1 more electron to anything. It's just going to form a sodium plus 1 ion. If that other thing needs 2 electrons, there will be another sodium atom that will give its electron to it. So it can be a -2 if that's what it needs, like oxygen, for example. You would just react 2 sodiums. You're not going to react 1 to make a +2 sodium ion. Okay. Okay, I think we're good with that. I think I'll run this one through the PowerPoint, because if you look at the ionization potentials, we expected it to increase going across. The exception is group 3A and 6A, and we understand why. When I put the first 2 electrons in, they're going into S-type orbitals. If I go to boron, I've got 1 extra electron outside of that. And if I took that 1 electron away to make for this first ionization potential, what would be left behind is a helium configuration. And that's pretty good. It would like that. And so it makes it a little easier to take away that electron. You're going to leave 2 electrons paired up in the 1s orbital when you do that. So instead of boron being up here in line with these, it's down below. Then everything goes normal across the p orbital. That's a p1, p2, p3, but p4 is lower. Why? Because the p4 configuration required you to put one of that 4th electron paired up with one of the others. And if you, it's easy to get it out because it really doesn't want to be there. It had to pair up, and electrons are both negative, so they don't get along too well. All right. And you continue till you get to the neon across the first. Now, the reason why I wanted to reemphasize this is that is an exception that is almost always on standardized exams. I'd be surprised if it's not on your final as well. So you need to remember group 3A and 6A, their first ionization potential is not what you expect. Oops. Okay. I'll come back out. Okay. Now, let's, I'm going to go down and get this one too. Now, looking at the multiple ionization potentials, we mentioned that when you reach a noble gas configuration, that's very stable. Well, here's the magnesium example. When you take the first electron away, that's its first ionization potential, it takes very little energy to get that. The magnesium goes from magnesium is neon with a 3s2 configuration. Magnesium, you removed one of those electrons, it's neon 3s1. So now you go for the second ionization potential, which is to remove an electron from this one. Of course, the electron you're going to remove is that 3s1 configuration there. And it takes more energy to do that. Again, because the first ionization potential pulls a negative charge away from something that's neutral, whereas the second ionization potential pulls a negative charge from something that's already positive and attracts it by electrostatic attraction. Magnesium still has more electrons, so we can get more ionization potentials out, take an electron from that. Now, remember, this is a neon core. That's stable. Magnesium does not want to lose that electron, that next electron. And chemically, it will not do it. Because like I said before, if something else needs another electron from magnesium, just another magnesium atom will supply that electron, not the same one. One other one will. Because once you make the +2 ion, it won't react further. And here's why. Third ionization potential is way up here. You see this great huge gap that occurred when I broke the noble core. Now, this is a magnesium example. I could put any element across here I want to. It wouldn't be the first, second, and third, but the one that breaks the noble core will always be the highest one. Now, a little trick to remember is if I'm looking and I see this big gap, compared to this one, then I know here's where I broke the core. Magnesium is in group 2. The ionization potential that will be the biggest one is the next one. It's in group 2 because that produces a +2 ion and that produces a noble gas. The next one above that is going to be here. So any element you want, if I pick 10, for example, 10 is in group 4. Well, the first 3 would be ordinary, but the next one, no, let's see, first 4, 10 is in group 4. First 4 of them would be normal. They'd all go up from one to the next. But the 5th one is the one that's going to be way up here off the screen on this chart at this stage. So you can always tell the big gap occurs if you look at the element. This represents its normal position on the periodic chart. It's a group 2. This one is a group 2. 10 would be a group 4. So I would be normal till I got to group 4. It's a 4th ionization potential. Those would all be normal. The next one would be the 5th one in the case of 10. It would jump up real big. So I can look at this pattern and tell what element it is, or I can take the element and predict where this big jump will occur. So, okay. Now, electron affinity is it is easy to measure in a sense that is very well defined. It is the energy that is released when a species picks up an electron. So if it's a calorimetry experiment. I put that species into a calorimeter, I cause it to pick up an electron, and I measure the heat that came off. And that is the electron affinity. It's not easily predicted. I've got the trends here on the periodic chart. I just mentioned it because it is mentioned in the textbook and most other places, but it's not as useful to us other than it just fits the pattern that we expected. But it's hard to predict. Now, nitrogen, for example, nitrogen has 3 electrons in its p orbitals, 1 in each one of the 3. And we've learned that filled, empty, and half-filled shells are more stable. So nitrogen has a half-filled p orbital set. Now, you can give it another electron. There's a space for it to go. But it would have to pair up with one of the electrons that's already there, and those 2 electrons would repel each other. And so the energy it releases, in fact, the experimental value for the electron affinity of nitrogen is 0. It will take that electron. You can make it happen, but it's not going to give you any energy back for doing it. And so I think we would all predict, for example, from the fact that the nitrogen has a half-filled shell, that it would have a low electron affinity, but I don't know that anybody would have guessed it to be 0. Phosphorus isn't quite 0. So, and phosphorus is in the same family. So you can't predict it very well, and that's about all I'll have to say about it. All right. And I think these are problems, and that's okay. All right, let's take a minute out of here, and let's see if we can look at the practice exam, a practice quiz. It's coming up tomorrow. And let's get it big enough for you to see. Okay, and okay, and now let's do share screen so you can see it. Okay, let's first just take a really quick glance through. And this is what I would recommend as you take any of the exams, for me or anybody else. Just scan through it really quickly. Don't waste a lot of time, but just look at it and see what the questions are about. Because there might be something you can answer immediately. So I'm looking at the first one, calculate the wavelength of light. If 1.5 moles of photons has this much energy, and there are the constants that we need, that's going to be a rather difficult problem. I'm just going to make a mental note of what it's about, and I'm not going to try to answer it right now. I'm looking at this, and what is a possible symbol for an element with a Lewis dot structure shown below? That one we can answer. I know the way the dots go in. The first one goes in one place around the Lewis dot structure. The second one is paired up to it. The third one then goes into the p orbital. The fourth one goes into a different p orbital. The fifth one goes into the last of the 3 p orbitals. The sixth one has to pair up with one of those others. So there's 6 electrons in the valence. So this is group 6. And if you look on the periodic chart, it would be this one. And probably looking at this one, I would say, I know that one. I'll do it right now. So I'd do that one. Okay, the last electron in some atom has n equal to 4, L equal to 1, E equal to 0, S equal to -1/2. What atom is it? Okay, well, we can work through that. Not something I'm going to guess right away, though. How many unpaired electron spins does the cobalt atom have? Okay, we could get that one. And then number 5 is, again, a problem with now here's nomenclature. If you have learned this, then this is really easy. for example, I look at this formula, and in my head, immediately, it comes to permanganic acid. Now, how do I know that? Well, I know permanganate is MnO4 minus, and it's got one hydrogen, so that's what it has. Hydrogen's plus one, MnO4 is minus one. That has to be its formula. So all I got to do to make the acid is if that name, permanganate, ATE, if it ends in ATE, I just change it to IC, and I get permanganic acid. I'm answering that one on this first pass. And then I'm looking to this one, mercury 2 oxalate. Mercury 1 oxalate, I'm sorry. Mercury 1 oxalate is Hg2 plus 2. I memorized that. Oxalate is C2O4 2 minus. So this one has mercury 1 and oxalate. Mercury 1 is Hg2 with a plus 2. Oxalate is C2O4 with a minus 2. So the formula is Hg2, C2O4. And so again, I've got those two. So on this first pass, I got 3. And I hope you would do as well with that too. Now, these others, I need to gather some stuff around. Somehow or other, in my clutter, I've left my periodic chart somewhere else. So pull one over here so that you can see it. Okay, and then let's, I'll have that available now when I need it. And let's stop the screen share. And I hope you have a copy of this. I need to work through it with you with this over on the pad. Okay, now, it said calculate the wavelength if 1.5 moles of photons has an energy of 125 kilojoules. And then we've got the constants that we might need. So I'm going to say for number 1, I want the energy of a photon. And the energy of a photon is hc over lambda. If I have wavelength, and that's what it's asking for here, it would just be h times nu, the frequency, if it had given me the frequency. Now I'm going to calculate the wavelength, but before I do, I want to remind myself of something. The energy that I would get, if I had the wavelength given, the speed of light is given, Planck's constant is given, I would calculate the energy. What would the units be? The units would be joules per photon. Okay? So the energy is joules per photon. So I'm going to now solve for the wavelength. The wavelength then is going to be hc divided by E. Now, if I'm going to get the wavelength, the units I'm going to get is going to be meters because that's distance. And that is the unit for distance in the SI system. Now, here's what the problem is. The energy I put in is not given in the problem as joules per photon. It's given that 1.5 moles, 1.50 moles of photons has an energy of 125 kilojoules. And then it asks me for the wavelength. So I have to put in energy in joules per photon. Well, the energy, we can calculate that from the data that was given in the problem. The problem said we had 125 kilojoules. Kilo is 10 to the third joules. That's how much energy I've got. How many photons do I have? Well, I've got 1.5 moles. And each mole has Avogadro's number, 6.02 times 10 to the 23rd photons. Okay, so there is my energy in joules per photon. So here's, I'll go ahead and calculate this, and let's see what we get when we do that part of the problem. All right, we get 125 with an exponent of 3. I want to divide that by 1.5 and divide that by 6.02, second exponent 23. And now I'll check. I've got 125 exponent third divided by 1.5 and divided by 6.02 times. Okay, it looks like that's right. So what I'm coming out with is the energy is going to be 1.384 and a whole bunch of other digits times 10 minus 19. I'm writing all this down for your benefit. If I were working this problem, I wouldn't have written any of this stuff down and then copy it back in. And definitely here, and you shouldn't do it either, do not copy this down and re-enter it in your calculator. Here's what we do instead. I'm going to take Planck's constant times the speed of light and divide by this. I've already divided by this. I've already got this calculated over here. So all I got to do is divide when I get to that stage. So my wavelength is going to be the Planck's constant, and it's 6.626 with an exponent of negative 34. I want to multiply that by the speed of light. It's 3 with an exponent of 8. 3.00 times 10 to the 8th. And now I'm double checking my number. I do have 6.626 times 10 to the negative 34 times 3 times 10 to the 8th. Now I want to divide by my answer. And what I come out with is my wavelength I've calculated to be 1.4359 and a whole bunch of other digits times 10 to the minus 6. Now, what do we say the unit was? That's right, it's meters. I'm looking at my answers, they're not in meters. So I've got to convert from meters to nanometers. So here's what I'm going to do. Our way of conversion is always, I've got a number with a unit. And I'll put that unit here. I'll put the unit I want up here. Now, nanometers, I've got a 10 to the negative 9 in that nanometers. So I need a 10 to the negative 9 down here. And so 1 nanometer and 1 nanometer. See, it's the same thing. So my meters are going to cancel. And if I divide my answer by 10 to the negative 9, still on my calculator, so I want to divide it by 1 with an exponent of negative 9. And I get 1.44. Yes, I get 1,440 when I round off to 3 significant figures, nanometers, and that would be 1.44 times 10 to the third nanometers as my final answer. Okay, and that is response C.
Mr. Pearson, can I
Yes.
see your calculator just for a second? I want to take a picture of the calculations, if you don't mind.
Can you
Just so
see?
I can
Can you,
Yeah, for
I don't know
kind,
whether you can see that or not.
hold on.
Let me see if I can pull it up a little closer, if I can do it without shaking.
Oh, that's perfect, actually. Thank you
Okay,
so much. Thank you.
all right, good. All right, you're right to be concerned about that, because the thing that takes people so much time on exams is writing down stuff and re-entering it. And I will guarantee you, if I do that on a whole test, there's going to be at least one of them somewhere in there. I've transposed a couple of digits, and it's going to just, I probably would recover from that, but it would take me time, and time is not your friend on exams and quizzes. You want to minimize the amount of time that you use so that you've got enough time to actually work the problems out. Okay, we've said we knew how to do number 2 already. So let's look at number 3 and see what it's about. It's the quantum numbers of the last electron that was added in an electron configuration. And we have n is equal to 4. We have L is equal to 1. We have M is equal to 0. And we have the spin is equal to minus 1/2. Now, I'm going to actually look at this number first. It's negative. Now, what did that tell me? It told me that I got to that electron by going all the way across an orbital and coming back, because the spin is down. So let's see what we've got. N is 4, and L is 1. So we are filling the 4p set, and p orbitals look like this. You're going to have a plus 1 m value, a 0, and a minus 1. Now, you need to remember how we did that back way on the checkpoint and so forth. Now, here's where the minus 1/2 comes in. The first electron goes like that. The second one goes in with the spin up. The third one goes in with the spin up. This one goes in with a spin down, and this one goes in with a spin down. Now that's the electron we wanted. See, we've got N is 4, we've got L is 1, P, we've got M sub L is 0, and we got the spin is minus 1/2. So that identifies that electron. So that is the last electron for this particular atom. Which one is it? 1, 2, 3, 4, 5, 6. So it's a 4p6. That's not the way we would need to write it out, but if we get a periodic table, we can figure out which one that is. Okay, so this is row 1, 2, 3, 4. We're in the 4s here and the 4p there. Remember, this would be 3D, but we're looking in the p orbital set across. And it's the 4th row. So this is P1, P2, P3, P4. Wait, what did I do? I'm off by 1. There it is. There's P1, P2, P3, P4, P5. So we've got, wait, what did I say? Couldn't be P6. I counted them wrong. 1, 2, 3, 4, 5. Oh, Earl. I need my coffee, folks. Okay. All right, we got it right now. 1, 2, 3, 4, 5, P5. All right. So it's 4p5, and that makes it bromine. So we're good with that. Now, the next one we're dealing with cobalt, and we want to know the noble core and how many electrons we would have in the cobalt atom. So let's look at the periodic chart first so we can see where we are. And if you Let's see if I can get a little better light on it. Well, maybe not. Cobalt is this element right here that I'm pointing to. Okay, now there is, I want the noble core. So it's this one up here. So it's going to be argon. It's go up a row and over to the end. So it's argon. So argon is my core. Okay, I'm looking at the answers now on that quiz. I just eliminated B. B had a krypton core. So it's not B, but we got an argon core. And then what do we have after that? We have 4s with 2. And what else have we got? Then we got 1, 2, 3, 4, 5, 6, 7. So it's going to be a 3d 7. So now let's see how many unpaired electrons we have. We've already got this. The 4s2 is all paired up, so we don't need to worry about it. 1, 2, 3, 4, 5. So we're looking at the 3D, and we want to put 7 electrons in it, plus 2, plus 1, 0, minus 1, and minus 2. I've got 7. 1, 2, 3, 4, 5, 6, 7. So there's my answer. It's an argon core with 3 unpaired electrons. And that would be C. Okay, now it says calculate the relativistic mass of 2.5 moles of photons with a wavelength of 540 nanometers. Okay, well, first thing we got to say is, okay, relativistic mass. That's the de Broglie equation. Lambda is equal to H over MC if it's photons. Now, if this problem had been about electrons or some other particle, then it wouldn't be C, it would be the velocity of that particle. So now, the wavelength we're given, we can calculate the mass. The mass then is going to be H over lambda times C if we solve for mass. Okay, now we've got everything we want. We got Planck's constant, we got the speed of light, and we got the wavelength given. So let's plug in the numbers. The mass is going to be the Planck's constant, and that was 6.626 times 10 negative 34 joule seconds. The wavelength is 540 times 10 minus 9. Where did I get that? You're right, nanometers. I've replaced nano, so I would have the right one. Speed of light is times 3.00 times 10 to the 8th. Now, what did I get? I got kilograms per photon. Remember, when I'm solving for the mass unit is kilograms, but I'm solving it for one wavelength of the light. That's one photon. So that's going to be the mass of one photon when I get to here. Let's go ahead and do the math with you. I'll clear my screen so I get all that extra stuff off. All right, 6.626 with an exponent, that's negative 34. Now that's that. I want to divide that by 540. Exponent is negative 9. And notice I did not write that into the standard form and change that power. I used the number that was given in the problem. It's less likely that I'll make a mistake if I do that. 540, and then I want to divide that by 3 with an exponent of 8. So if I'm looking at my screen, 6.626 times 10 negative 34 divided by 540 exponent. Oh, I made a mistake. I put in 9 instead of negative 9. No, I'm sorry. Okay. And so I need to go up there and see if I can repair that damage. I want to insert negative. Now let's see. Go back down here. Now we read it again. 6.626 times 10 negative 34 divided by 540 exponent negative 9 divided by 3 times 10 to the 8th. Okay, it looks like that's set up correctly. So what my screen is showing is the mass is 4.09, some other digits, 0, 1, I'll give you some extra ones, times 10 to the negative 36 kilograms per photon. Okay, now this said for 2.5 moles of that light. So, and the answer is given not in grams, it's given not in kilograms. Well, let's go ahead and do the photons, and then I'll get rid of I'll do the conversion from kilograms all the way over to nanograms. Okay, the number of photons is 1.5 moles. No, I'm sorry, it's 2.5 moles. 1.5 moles in the previous problem. So it's 2.5 moles times Avogadro's number times 6.02 times 10 to the 23rd. Okay, so I've got this on my screen. Let's go ahead and do that. I'm going to say times 2.5 and then times 6.02 with an exponent of 23. Oops, I get set up correctly. Okay, so I'm coming out now with 6.155 and the whole some other digits times 10 to the minus 12. Now it's kilograms, so I'm going to get rid of kilo and put a 10 to the third grams. Now I have to convert to match the answers of the problem from grams to nanograms. Nano is 10 to the minus 9, so I need a 10 to the minus 9 down here. Okay. Now, so I need to multiply by 10 to the third. And I need to divide it by 1 with an exponent of minus 9. And I'm coming up with 6.16 nanograms. Okay, that's good. That's D. So chances are if we got the answer on the test to plus or minus 1 and that significant figure on the right, I probably got it right. And we're done. Okay. Any questions now about it?
I have a quick question.
Sure.
For the formulas, when I was solving these equations, I was struggling to figure out which equation to use for each wavelength formula. Is there
Okay.
you can find like the list of all the different wavelength formulas? I just get lost with those.
Okay. Now there's this relationship, lambda times nu is equal to c. That's going to deal with changing from frequency to wavelength or wavelength to frequency, and we did a checkpoint on that. There is E is equal to H nu. That's if you're converting, you're determining the energy of a certain frequency of light, or there's the energy can also be expressed as we did up there, hc divided by lambda. And that again is converting between energy and wavelength. If you have a particle traveling at, or a photon traveling at the speed of light, c. So these two are the same. Nu is just take this equation here and solve for nu and place it in, and I get c over lambda. So these two equations really are the same, but they deal with changing between energy and wavelength. And then there's the de Broglie relationships that we have, and that's wavelength is equal to h c h over m c if it's a photon, or if it's a particle like an electron or a neutron or something, it's h over m v, where v is the velocity of the particle, how fast it's moving. Can't think of any other equations that we have on this unit that deals with that.
Okay, that's exactly what I was looking for. So thank you.
Okay, very good. And you do, at this stage, you do have to have these equations in mind. I don't give them to you on quizzes and or exams for that matter. I do give them to you on final exams and things like that, because but I want you to know the details as we're going through the detailed part of the course. When we get to the what do I really want you to take to the next course, I don't necessarily need you to memorize all that stuff. I want you to say, I don't remember the formula, but I know exactly where to find it in the textbook. That's what happens as you get further and further in education. It's not so much how much you can cram into your head, it's how much you can generate on your own, having your own resources, textbook, Google, but that's kind of down on the bottom of my list because I found too many mistakes out there. All right, are we good?
Dr. Pearson,
Yes.
I had a really quick question. I don't know if you can go back, but it's not on the quiz. It was one of the questions in the PowerPoint, and it was for one of these types of equations where you're calculating for mass. It was at the end. It was talking about the smallest mass of our analytical balance, and the lab can weigh like 0.0001 grams, and it's talking about like finding how many moles would be in that light.
Okay. Can you give me the numbers? I remember the problem. The mass, the smallest mass that we can weigh on a balance is plus or minus 0.0001 grams.
Yes.
Now that's what we have in on the that we can weigh on the balance. And again, we were trying to get a relationship between mass and the number of photons. So again, the wavelength of light is h over mc. So I need to put the mass in here for a certain number of photons. Or if I'm solving the other way around, I can say, okay, well, mass is equal to h over lambda times c. And I'd say, okay, if I put these numbers in, I will get the mass of one photon. And that can become a conversion factor to convert this number of grams into photons, numbers of photons. I don't remember the problem, but let's suppose the wavelength of the light was 650 nanometers. And I want to know how many photons, or maybe moles of photons, or how many photons would this many grams correspond to. So how many photons has 10 to the negative 4 for its mass? All right, let's put the numbers in. H is 6.626 times 10 to the negative 34. The wavelength we want is 650 times 10 minus 9 meters, 650 nanometers. Speed of light, 3 times 10 to the 8th. And this is going to be mass. So again, let's put our numbers in. 6.626 with an exponent of negative 34. I want to divide that by 650 with an exponent of negative 9. And I want to divide that by 3 with an exponent of 8. That looks okay. And in this case, I get a mass is equal to 3.3979 and some more digits times 10 to the minus 36. Have you guys noticed when I put those numbers in, I copy this down for you to see, but I'm using the whole digit and doing the calculation. And when I get to round off, I'm going to round off only the final answer that I get. And you need to get used to doing it that way. That's the way you want to always do problems. The last thing you do before you write your answer and present it to somebody else is round it to the proper number of significant figures. And that's done as the very last operation. Now, what did I get? I got kilograms for 1 photon. Okay, I want to know grams, so I'm going to change grams to kilograms, and I can do that real easy. Just change the kilo to 10 to the 3rd. So when I do that math, I'm going to get the mass is 3.3979 and all those digits times 10 to the negative 33 grams for 1 photon. Now, there's my mass. My mass is 0.0001 grams. And I've got a conversion factor. 1 photon has a mass of 3.3979 in digits times 10 to the negative 33 grams. Now my gram units will cancel. So if I take this number I've got on my, I'm trying to convert, so I'm going to take that number and divide by the answer that's still on my screen. So I take 0.0001, divide by my answer, and I'm coming out with 2.943 times 10 to the 31st photons. Now, if I wanted to convert that to moles and see how many moles that were, then all I do is change from photons to moles of photons. And 1 mole is 6.02 times 10 to the 23rd photons. So I just need to divide that number by Avogadro's number. So I divide it by 6.02 with an exponent of 23. And I've come out with a number like 48.9 times 10. Let's see, 1, 2, 3, 4, 5, 6, 7, 48, 4.8 9 times 10 to the 7th moles of photons. I think that's right. 1, 2, 3, 4, 5, 6, 7. Yes. Okay. All right. So that may not be the exact wavelength and problems that was on the PowerPoint, but that's the way it should have been worked. Is that okay with you?
Yeah, it works. And you chose that equation because we're talking about photons, so it wouldn't be h over mv, it'd be h over mc because we're talking about
Exactly.
photons. Okay.
This unit told me I want mass of light, and that should have triggered me to remember this equation, the de Broglie wavelength equation. And then that's how I knew to go solving for mass. And the key feature along the way is when I solve for mass, I got to know what I got. And mass is in kilograms. So if you put these units in the correct unit, just the ones that were given were SI units. If you put them in SI units and do the math, the number on your screen has the unit of kilograms. And so that gave me my units on my answer when I got to the stage here. And then I converted from grams to kilograms to grams in this step. And now I had grams per photon. I needed to do that because the problem wanted to know how many photons for this many grams. So I needed my conversion factor here. I would do it this way. There's certainly other ways to go about doing this, but I don't think the other ways are as straightforward. I've got a number that's got a unit, and I need a conversion to another unit. So I'm going to think of a relationship that gives me that conversion factor. And then I'm going to make that conversion factor have this unit so I can make it cancel. And then I just do a regular conversion factor. This part of the problem down here is no more than saying, well, how many inches are there in 38.6 meters or centimeters or whatever? It's the same kind of problem. You need a conversion factor. Okay? All right. Are we good? Okay. Let's go back, and I'm going to pause the recording. Okay. Okay. We're looking more detail now at bonding in this one. And the type of bonding that we've seen a lot of so far, almost everything we've done, has been with ionic compounds. And the type of bonding for ionic compounds is really pretty simple to understand. It's just electrostatic attraction. A positive ion will attract a negative ion no matter how far they are apart, unless it's infinite, whatever that means. But it'll get to the point where, as if I pull the charges apart, say put a positive charge and a negative charge together, and if I pull that all the way out to, quote, infinity, then there would be a fixed amount of energy it would take to separate those two charges. And it would be the work or energy done in separating them. If I started looking at that as I pull them apart, it's going to make a big difference. It's going to take a lot of energy to pull those charges apart when they're really, really close together. And maybe by the time I get them a few hundred diameters away, I've already used up most of the energy it's going to take them all the way out to infinity. So the nature of electrostatic forces is that, yes, they attract each other from great distances, and they are going to start drifting toward each other. But as they get closer and closer together, that force grows up dramatically so that they are really hard to get apart when they're touching. And if we start the Now, if you imagine positive and negative ions, I've shown them here, little circles with red charges inside. If you put them together, what's going to happen is you're going to build a pattern like this. If I just took two charges and brought them together, they would come together till they touch. Now, if I brought a third one in, imagine your two hands in front of you. Your left hand is positive, left fist is positive, your right fist is negative, and you're putting them exactly touching each other. Now, if you imagine bringing another positive ion in, I said your right fist was negative, so the new positive ion you're bringing in, no matter where it's located, is going to feel a little bit stronger attraction for the negative charge than it feels repulsion from the positive charge. So it's going to be attracted toward that negative charge. So when I get them together so that two of them touch, then I can imagine this third one rolling around here on my right fist and getting as far away from the other one as possible. And this is what you would see. These three ions would line up like this: a negative, a positive. The next negative one that came in and hit this one somewhere would wind up opposite it. And this would happen for all of them down the line. When the next one came in, this positive ion would be next to that negative ion, and then there would be a negative ion attached to it, and so forth. And we would build this kind of structure. It's a very stable structure, and it takes an awful lot of energy to remove or to break it apart. Let's imagine right here in the middle, and look, there's a positive ion. How many negative ions are actually touching the one I have my cursor on right now, this one? You said 4? No, there's 6. Where's the other two? One above and one below. I'm just showing a slice through the crystal that would form. It's three-dimensional, and every ion in there, the one I had was positive here, and it had 6 negative ones around it. If I concentrate on this one, it's negative, but it's got 6 other positive ions directly touching it. So every ion in there is surrounded by 6 other ions of the opposite charge. We would say this has a coordination number of 6. There's 6 things attached to each particle inside that three-dimensional structure. Now look at this line separating that. I can imagine this line going right down through the crystal. What do you see? You see a negative ion on this side, a positive on this one, a negative here, a positive here. The ions right on either side of that line are oppositely charged. So there would be strong attraction. Now imagine I took a razor blade. Now this is the sharp side. Think about it. We're talking atomic dimensions here. Okay. You put this razor blade on that crystal and you tap it and just push it down the diameter of one crystal, 1 unit. Now look what happens. Now remember, I have only moved that crystal down 1 atomic diameter. That's of the order of a few nanometers. And I went from strong attraction to now strong repulsion. This atom and this one repel each other, that one and that one and that one and that one. All the ions repel each other right down that blue line now where the razor blade moved one side of the crystal down. What happens? It's going to come apart just like that. And it'll come apart and you'll have 2 pieces. This is called cleavage of crystals. And crystals have the ability to be cleaved in lots of directions. Now I showed you just this vertical cleavage plane, but you know, you could go down through any set of atoms. You see, there's a line of ions at this angle. And there's, I could go over by 2 each time, and there would be a line of atoms that line up across a line. So there's lots of possible cleavage planes in crystals. And as long as you tap along one of those cleavage planes, you get a clean separation. Now think about what this is really going to look like. That separation, the way I'm showing it here, has every single atom in a line. That's going to be a sharper edge than you can even imagine, to have everything smooth to distances in the order of nanometers. Now, I'll tell you a story here. I told you on my Who Am I file, I worked with NASA for several summers on some research with them. And NASA, if a contractor supplied parts to NASA, they had to make sure they were as near perfect as possible. So very early in the space program, they needed to move things when they were out in space. So they needed motors to do that. They could control the motors from down here on Earth and move things around up in the space capsules. So they figured they needed perfect bearings in those motors. So the specifications were the motors had to be so smooth, the bearings in them had to be so smooth, they had to be smooth to a few nanometers, a few wavelengths of light. That's how we reflect off surfaces and tell whether they're smooth or not, is by using light of a certain wavelength. And the way we see it reflected off, we can tell how smooth that surface is. So it had to have no imperfections within a quarter of the wavelength of some visible light beam. So they made them like that. The bearings were all smooth spheres to that smoothness. The races that the bearing rolls in, the other part of the bearing, had to be smooth to a quarter of the wavelength of light. So they produced bearings and motors down here that were absolutely perfect. And so they take it and put it in the spacecraft, put it up in space. They turn the motor on and it goes and stopped, locked up, every one of the motors. Did just a fraction of a turn before they became perfectly frozen and would not work anymore. They brought the motors back down to inspect them to see what in the world had happened. What they found is all of the bearings were fused together as if they were one piece of metal. And you think, well, how could that happen? Well, let's run this in reverse and see what happens. If you bring them close together and slide them, you know, now like in the case of the bearing, they turned it on. When it just started up and went a little bit further, you know, coming back. Now let's go backward as they start to move, and maybe they're in this position when the race and the bearing are touching each other. They turn it on and it moves to this position and becomes one single crystal. So that's what happened. The bearing and the races that held them became one piece of metal because of a process that we've now termed optically contacting. And we've made great use of that. A lot of the stuff that was done during the space program for NASA have become commercial possibilities. And this is one of them. If you want to contact any surface, you just take that rough edge of the two pieces you want to put together, and you smooth them down to atomic dimensions so that there are no little peaks and valleys hardly at all in the two surfaces. Then you hold one of them stationary and you put the other one on a device called a goniometer that allows you to move things extremely slow at distances corresponding to the wavelengths of light. And when you slide those two pieces together so that the atoms line up again, it's as if they had never been taken apart. So we can glue things together now into one piece of metal or glass or plastic, whatever. We can put them together as if they were one piece just because of what you're seeing here. And why didn't that happen on Earth? Well, on Earth, you're in an atmosphere. Evidently, somebody didn't do the obvious experiment before they sent it up. They must not have tried it in a vacuum. But on Earth, everything is covered with air. Air molecules are sticking to things. So whenever they had those races and the bearings in an Earth atmosphere, the surfaces were covered with everything, air, nitrogen, oxygen, water vapor. All of those things were inside that space between. So the race and the bearing were never really in contact here on Earth. But when you went into space and you suck the air out, then you get this to happen. So this really does occur, and it will. This is what you get for crystalline ionic compounds, or really any crystal will do that same thing. The other type of bonding that is more common to us for chemicals and for chemistry is building molecules. And we do that with the covalent bonding. It's sharing of a pair, P-A-I-R, pair of electrons. That's crucial. It's a pair of electrons that are shared. And when you bond things like that, these are typically non-metal compounds. So when you put those things together, the low molecular covalent compounds are apt to be gases at room temperature if they're low molecular weight. If they're moderate molecular weights, they're apt to be liquids. If they're high molecular weights, they're apt to be solids, like low molecular weight carbon dioxide. Gasoline would have a high molecular weight, and paraffin wax would have a much higher molecular weight. And they would be gases and liquids and solids in that order. Now, I deliberately left out water. Water is a liquid at room temperature, and if it were bonded the way carbon dioxide is, water would be a gas at room temperature or at temperatures way below freezing even. It would be gas. But water is unusual because of its shape, and it's unusual because it has to be that way if you're going to have liquid water. If you're going to make liquid water where life can exist, and all of life as we know it is based on liquid water being inside your cells and inside the trees and everything else that we see around us here. And it depends on the fact that water is a liquid at room temperature, and it shouldn't be, according to what we know so far. And Gen Chem 2 will go into much greater detail about that and be able to understand exactly why water is a liquid at room temperature. Metallic bonding deals with metals. Metals are solids. What do you know about metals? You can bend them and stretch them and they're very good electrical conductors and very good conductors of heat. And the metals bond in a way that we describe as an electron sea. metal atoms, the outside electron is so easily removed that when you put two metal atoms close to each other, they're apt to stick together and the electrons of one will migrate around both. And here shows a picture of a large sample, perhaps, of some metal. And you can think of it, if this is sodium metal, then you've got sodium ions just randomly scattered out in a sea that's just uniform charge caused by all the electrons. So the electrons that I'm showing close to some particular atom is not really, doesn't really belong to that atom. Instead, the electrons are bathed in a sea, the cations are bathed in a sea of electrons. So that's the reason why I can put these positive charges in this metal, the cation part of the metal, anywhere I want to, because any environment I put it in is a negative C. So it doesn't really matter unless they're really, really close to each other. Of course, this one and this one might repel each other, but they can move out of the way and they can minimize the forces of repulsion between each one of them and assume whatever shape you put it in. If it's like this, it's okay. If I want to make it stretch it or pull it, I can do that. If I put a pair of electrons on it, on a battery, you've got a negative pole and a positive pole. And the negative pole is, well, a battery is an electron pump. What it does is there's some chemical reactions going on inside, and they're configured in a way that you pull electrons away from one end of the battery and put them on the other end of the battery. So that's what happens, and it's sitting there with that permanent charge as long as the battery hasn't been discharged. One end's going to be negative and the other end is positive. Now, if you stick those two ends to a metal, what will happen is the negative charge on the electrode will move into that C, and at nearly the speed of light, the same number of electrons pop out the other side and neutralize the charge on the other electrode. So you see a current flow. And the electrons that popped in are not the electrons that popped out. The electrons that popped out were the ones that are over here on this side already. And as soon as you put the excess charge in there, that's unstable. You got too much negative charge, so it's going to hop off the wire on this side. That's why metals are good conductors of electricity, and they're good conductors of heat, because if I put heat energy in here, the electrons on this side is in this C, they start vibrating with the energy that current had going in, and that moves it all the way to the other side. Or if I've got heat energy, the thermal energy, the random molecular motion hitting these electrons on this side would transfer that heat right down the line to the other side. So metals are good electrical conductors, are good heat conductors, and we think that's true because the metals are bonded in this electron C type of configuration. Oopsie daisy, back up. Okay, we talked about valence electrons already. They're the ones that are typically going to have the highest N number. Excuse me. So on the outside of any atom, when we build their electron configuration, it's going to have s and p orbitals outside, and the ones with the highest N value are the biggest ones. So in the transition metals, we've mentioned this before, the transition metals have 4s2 configuration, 3d something. Well, the 4s fills before the 3d, but the 4s is bigger than the 3d. So all the transition elements have these two electrons on the outside, and those electrons and any partially filled electrons are valence electrons in that atom. And since there's s and p orbitals on the outside of every atom, the maximum any atom can have in its outside layer, not in its valence shell. Now you got to understand the valence shell includes the outside layer plus the ones under it that are not filled. So the outside layer can't hold more than 8 electrons. And that is the so-called octet rule. And that's the arrangement of the noble gases. And so atoms tend to lose or gain electrons to get an octet rule. Yeah. We've done this already back earlier, so let's go through quickly. If I've got 5 electrons in a Lewis dot structure, what I'm trying to show is 1 electron, 2 of the electrons were in the s orbital, that's those 2. Remember that 2 could be here or here or here as well, it wouldn't matter. And 1 electron in each of the other. The important thing about group 5, nitrogen and its family, is 1 pair of electrons is paired up and 3 are unpaired. You can have ionic bonding by losing all 5 of those electrons, or you could gain 3 more. Nitrogen's more likely to gain 3 more. How do I know 3? Because there's a space here and here and here for electrons. Now that gives me 8 on the outside, and that would be a noble gas configuration. Neon. So I could have nitrogen as a -3 or a +5. My guess it would be -3 if it's going to be ionic. And not the +5. The +5 would just take them all away. Now it can also share 3 electrons, and that's covalent bonding. So I can have an atom that wants to hang on to its electron like another nonmetal, and it can donate electron into here. And that pair of electrons then can be shared by that atom and this atom that's bonded to it. So I can have an electron sharing occurring here, or here, or here. So nitrogen can form single bonds, pairs of electrons bonded between it and another atom. In ammonia, this atom would be hydrogen and hydrogen and hydrogen. The correct formula for ammonia is NH3. And it's not ionic because it doesn't have ionic properties. Nitrogen as ammonia as a gas at room temperature. So it has 3 covalent bonds linking the hydrogens together. We talked about the energy to break an ionic compound apart. It's called the lattice energy. And if I'm looking at the lattice energy and trying to imagine what affects it, if I've got small ions, that means they get close together. The closer they are, the stronger the force is between them. So small ions are going to have much higher lattice energy than large atoms would have because they start out further apart and with the force weaker between them. What about the charge? Compare 2 atoms of the same size, but let's say one of them is a +2, the other one is a +1. Well, obviously the +2 has a stronger attraction for negative charge than the +1 does. So the larger the charge and the smaller the ion, the higher the lattice energy is going to be. Now, when you build electron configurations for ions, here's a very, very important thing. Now, the anion is easy because all you're going to do, if you're taking, let's say, oxygen, it's in group 6. If I'm going to add 2 more electrons to it, it's going to move over and have the same electron configuration that neon would have. And it would gain 2 electrons. So I could get that configuration for the anions just by doing the element. If it's -2, just do the element 2 rows over. If it's -3, do the element that's 3 rows columns over, and so forth. But you can't do that for cations. Remember to do a cation, to produce a cation, you have to remove an electron. Now think physically how that has to happen. Again, hold your two fists in front of you and see, okay, how can I get an electron to come off of this metal and go on to that non-metal? If I'm holding my fists a foot apart, that can't happen, can it? What has to happen? They have to come together until, like you bring your two fists together, they have to come together until they actually touch. Now, when they touch, what touched? The most outside atoms touched, electrons touched each other. That's the one with the highest N value. So if I'm doing two transition elements or a transition element reacting with something else, the transition element has 4s2 on its outside. And then it has some d orbitals underneath that. And when that transition element bumps into another element, say a chlorine atom from outside, it hits the 4s2. And it's going to take those out first. So those two are going to come out first. So any of the transition metals, say I have nickel. Nickel's got 4s2 and then 3d8, I think, underneath it. The 4s2 comes out first. So if chlorine comes in and hits nickel, what's it going to do? Chlorine needs one more electron. It's going to take one electron from that nickel atom and make chloride ion. Another chlorine can come in, hit that same nickel ion, take a second electron away, and make Ni+2, that's stable, and 2 Cl minuses. So it's going to make nickel 2 chloride, NiCl2. You remove the electrons from the outside first. So in order to get the electron configuration of a cation, you first build the neutral atoms, electron configuration, look for the place where you've got the highest N number, take those electrons out first. So you go from highest N number to the next highest N number. If you got all of them, you'd still go down the list like that by size. So remember, the outside of atoms is always s and p orbitals. If there's unfilled shells, they're always underneath that. The transition elements are the next layer down. If I go across all the way to the noble gas elements, to the rare earth elements, say uranium, when I go out there, there's actually 3 levels deep. So the valence shell for uranium is the first part of the valence shell is the s electrons on the outside. The next one is going to have 1d electron, 1 layer in. And when we go to uranium, it's going to have, I don't have the chart in front of my head, but it's like the 3rd or 4th element across. Let's see, I'll look. It's the 3rd element across, so it's going to have an F3 configuration down there. So you have to go all the way in, 2 layers deep to get down to the other elements. So if I'm taking uranium, the first electron is going to come out of that s orbital. The second electron is going to come out of that s orbital. The third electron is going to come out of a d orbital. The 4th and higher electrons are going to come out of the 4f, 5f level in that case of uranium. So remember, we're taking electrons one at a time, outside to inside, not the order they filled, but from outside to inside. There's one of the biggest mistakes in this unit is to get that wrong. So think about that and remember that. Make a special note. Now, typically in sizes, cations are smaller than neutral and anions are larger than neutral would be. Does that make sense? If it's a cation, it's got more protons in its nucleus than it has electrons. So the electrons are going to be pulled in really hard. If it's an anion, it's got more electrons than protons. And so the electrons won't be pulled in as much because the electrons repel each other more and more as you start pulling them toward the nucleus. They're getting closer and closer together. So cations are going to be the smallest, anions are going to be the largest, neutrals are going to be the ones in between. Now, I should preface that by saying we're talking about if they have the same noble gas core. That's going to be true. If they have different noble gas cores, I'm not even going to look at the charge. The bigger the core, the bigger the ion, whether it's positive, negative, or neutral, is not as important as the size of the core. So, and remember, as I go down on any element, down any column, the ones near the bottom have the bigger noble gas core. Okay, now, when you have covalent bonding, here again, I'll ask you to do an exercise with me with your hands. Take your thumb and your first two fingers on each hand and spread them apart and hold the other two, the pinky and the ring finger, down next to your hand. Now we're going to imagine bonding. When you bring atoms together, bring your thumbs together so that they match. Now that's a single bond. One pair of electrons shared between two atoms, one represented by your left hand, the other one by your right hand. So you have a single bond. Now, bring your two index fingers together, okay? Now you've got two pairs of electrons shared. That's a double bond. And one pair of electrons that's not being shared this way, okay? Now, bring the other two fingers together now. Now you've got your thumbs together, your top index fingers together, and your second finger together. That's a triple bond. Now, so you can get single, double, and triple. Now, why don't you have a quadruple bond possible? Well, look at where your elbows are pointing. That would be the direction of the other pair of electrons on each one of those atoms. There's no way you can pull them together in line and make them contact with the two atoms. So you can have single bonds, double bonds, or triple bonds, but you can't have a quadruple bond. Now, just imagine, which is stronger, a single bond or a double bond? Well, it makes sense, right? It's a double bond. If I'm sharing one pair of electrons between two atoms, and that's holding them together, sharing two pairs would be stronger. It won't be twice as strong, but it'll be stronger than a single bond. And the triple bond is the strongest yet. In fact, the nitrogen to nitrogen triple bond is the strongest bond that we can imagine. And I may have mentioned this to you in the past, but in our general discussions about the way nature works for us, nitrogen N2 is so strong, it takes temperatures of a lightning bolt, hundreds and thousands of degrees, to break apart the nitrogen molecule into individual atoms. So that means I can put nitrogen in the atmosphere to dilute the oxygen and make it a breathable mixture for us. And at the same time, the nitrogen as a diluent, every time lightning strikes through the air, it's going to break the nitrogen molecule apart. It's going to react with oxygen. The nitrogen oxides are going to dissolve in the rainwater. It's going to wash down to the soil and fertilize the plants with nitrates. So this bonding is critical for that to happen. And it's critical for that process to take place to produce a fertilizer for the plants that we need to eat and animals need to eat. So the whole ecosystem that we have is based on this fact that nitrogen forms an extremely strong bond with itself, and it forms that triple bond. There are very few bonds that chemists have ever been able to make stronger than the nitrogen to nitrogen triple bond. It's extremely difficult to find anything that strong in the way of bonding. Now, when electrons are shared between atoms, they are not shared equally. Now, remember when I talked to you very first day, I talked about the nature of everything being particulate and how the atoms of one element were all very similar chemically, but different from each other. They differ in their size. We've talked about that. They differ in their shape. We mentioned that in the case of water being shaped a certain way around the oxygen atom. That causes it to be bent. That causes it to share electrons unequally. And the third point I said, the atoms have different sizes, they have different shapes, and differences in the way they attract charges to themselves. Those characteristics really are behind all of the things that we see around us. They're all made and all pre-programmed to be able to make that at the moment they were created. An atom, a nitrogen atom now is just like the ones that were formed at creation. In fact, every single one that was formed then is still here unless it's undergone some kind of nuclear process. Chemistry doesn't change atoms, remember, it just changes their partners. So the nitrogen and oxygen, all of those elements differ in the way they share electrons. Their shape determines how many pairs. For example, carbon can do all four of those. When we had our fingers together, and I had my thumb and my index finger, my first finger all touching each other, representing a triple bond. Well, carbon can form single bonds, it can form double bonds, and it can form triple bonds with itself. It can't form a quadruple bond, neither can any other atom. But carbon has that kind of variable shape that makes it critical to have the properties carbon atoms have. And the key feature for carbon atoms is that they can bond with themselves to thousands and thousands of carbon atoms in a single molecule. The plastic pen that you saw me writing with a while ago, that plastic is in chains of carbon atoms that are hundreds of thousands of carbon atoms stuck together. That unique characteristic is unique to carbon. But they're not shared equally. Non-metals and metals, okay? Which do you think would have a stronger attraction for electrons? Now think about it. What happens to metals when they react? Right? They lose their electron. What happens to non-metals? Yep, they are the ones that gain them. Okay, so if electrons gain electrons, do you think if non-metals gain electrons, don't you think they have a stronger attraction for electrons than metals? This stuff all makes sense. It really does. Now, the attraction that an atom has for its own valence electrons, or electrons that penetrate its valence shell due to bonding, covalent bonding, the electrons in its valence shell are attracted to that atom by this term we call electronegativity. So when I talked about atoms having a particular size, a particular shape, and an attraction for electrons, this is the word that we use for that attraction for electrons, electronegativity. And now let's look at the trends. We know non-metals are more electronegative than metals. Don't memorize both ways, okay? You know, you didn't get as bald as I am and as wrinkled as I am without learning some things along the line. And one of them is never memorize both of two alternatives.
Graham's car over there.
Huh?
You're going to transition over to Graham's car.
Okay.
Because you're going to stay here until noon, right?
Okay, someone, you've got your mic on. If you want to converse with each other, it would be best if you did it through a text. You can do that still. Okay, fluorine is the most electronegative element because it's the smallest one of the atoms, neglecting helium. It's the smallest element on the chart. And fluorine is the most smallest next to that of any element up to it. I guess the corner of the periodic chart. It still has the highest electronegativity. Neon next to it would not have high electronegativity because it doesn't attract electrons. It doesn't want to give them up either, but it's happy with what it's got. So it has no attraction for electrons. But fluorine is extremely electronegative, the highest. The pattern from the periodic chart, well, let's look at it. And I want to give you some detailed numbers. This is in a scale due to Linus Pauling. I think it's not the one that's in your textbook, but I like this one. We're just looking at differences, so it doesn't matter which scale you actually use. And chemists can get into all kinds of arguments about how we should express it, but at the end of the day, the only thing that matters is the difference in the numbers, not the absolute numbers themselves. So this scale was developed by Pauling. It ranges from 0 to 4 on the electronegativity scale. And if you assign a 4 to fluorine, then the pattern is pretty easy to remember. Starts with lithium, it's a 1, and then 1.5, 2, 2.5, 3, 3.5, and 4. So it just counts by half from 1 to 4 across the first row of the representative elements. And now those are the only ones we're going to worry about electronegativities for. We're not worried about electronegativities of transition metals or intertransition elements as well. Now, so you do see a general trend, increase in electronegativity from the left to the right. So that is true on every column, every row on the periodic chart is like that. Now, I want some pivotal numbers. Phosphorus and hydrogen are equal. Now, this one you just have to memorize. This one just an easy pattern to regenerate. But phosphorus is equal to hydrogen, and it's 2.1. So phosphorus and hydrogen have the same attraction for electrons, same electronegativity. Chlorine and nitrogen have the same. So if you imagine moving over 1 and down 1, you get the chlorine to nitrogen, the same value. So while we didn't memorize chlorine, if I remember it's nitrogen, I can generate the pattern for nitrogen. So chlorine is 3 also. Now, if you look at iodine, it's the same as carbon. So now I'm skipping one here. I skipped one up here. I'm skipping one here. The next element is the same as, so iodine is the same as carbon. So while I might not memorize iodine, if I remember they're the same, like I've remembered chlorine and nitrogen, phosphorus and hydrogen are the same, then I know the value for chlorine and for iodine. I can get bromine because if this is a 3 and this is a 2.5, this is between the two. So if you average 2.5 and 3, you come out about 2.8. That is the correct value for bromine. So with this pattern now, I can generate most of the, say, okay, I didn't memorize, let's see, oxygen, sulfur would be the next row, and phosphorus is here. So sulfur, it would be right under oxygen. So it would be after phosphorus. So it's going to be more electronegative, more than 2.1. And it's going to be less than chlorine, which is 3. So it's going to be between 2.1 and 3. I could get the numbers and make an estimate, and that's okay. That's usually close enough for the kind of comparisons that we're doing. So I'm showing that you can use these values and sort of give an idea of where the next value would be, at least a ballpark figure of what it would be for the other elements on this end of the chart. And by the way, from carbon on down, really, in this little triangle is what we're most interested in. The compounds between atoms of nonmetals with each other. That's the most important. Now, if you go over here, I wanted to show you, if I go all the way down the column, it should get smaller, and it does. But look, from lithium all the way to cesium. Now, I left off francium because that stuff's radioactive. We don't deal with it. But it would be a little less than 0.7, but probably not a lot less. So you can see there's not much of a difference between the metals. You see, they're all in this range of low numbers, generally less than 1. Most of the other metals will be less than lithium, except when you get way over here to the lead. Well, for example, carbon down at the bottom of its family is lead. So it's not, it's going to be probably, I would guess, a little bigger than 1, but something close to 1. Usually something close to is all we need to know. All right, but this is a pattern that you really ought to learn. 1, 1.5, 2, 2.5, 3, 3.5, and 4. Phosphorus and hydrogen equal. Chlorine and nitrogen equal. Iodine and carbon equal. And with those pivotal points, you can make comparisons. Now, so this is, I want to wait on that just a second. I want to give you another quick little rule of thumb. Now, we've got these numbers memorized, right? We can get all of these numbers. So if I ask you to compare the electronegativity of carbon and beryllium and nitrogen and oxygen, you know, you can put these numbers in, you can tell exactly what the difference between nitrogen and oxygen is 0.5, with oxygen more electronegative. If I'm doing between carbon and beryllium, well, the difference is 1.0, with carbon being the more electronegative. So if I'm dealing with the first row, I'm good. It's dealing with these others that I don't, that makes it hard. Now, I've shown you some of the ways you can do it, but now this is important. If you're taking this down in notes, be sure that you remind yourself what I'm about to tell you only works for atoms outside the first row across. But if it's down here, if I'm comparing an element here with another one here, whichever one is closest to its end is the more electronegative of the two. So if I'm comparing this one with this one, whatever they two are, this one is closer to its row than this one. It's more electronegative than this one. So if you're, it makes it fairly easy then to make comparisons between elements on the chart down here, and that's where a lot of the comparisons take place, is just see which one is closest to its end row. The one that's closest to the end is the more electronegative of the two. Now, when you bond two atoms together that don't have the same electronegativity, the bond will be a polar covalent bond. Now, think about poles, the North Pole and the South Pole of the Earth. They're opposite charge, right? There's a North Pole and a South Pole. And the magnetic field of the Earth is distributed from north to south. And as you go down, say, to the equator, the electric field would be, a magnetic field would be effectively zero there. But there's a strong magnetic field, and the Earth is polar in its magnetic field. And that Earth is a really big magnet, and that's why your compass works. Your compass is a little tiny magnet balanced on a needle point, and the point that's marked north, it's going to point north. I mean, it's painted with a little N on it, but this, between me and you, it's actually the South Pole of that magnet. We don't need to know that. We just need to know that if that black mark points toward north, that's north. Wherever it's pointing, that's north of where you are. So, but there is a polar Earth. There's a when we talk about a polar molecule, we're talking about charge separation. The more electronegative atom is going to get more than its fair share, 50% of that pair of electrons. So more than 50% of the time, the pair of electrons are going to be in the vicinity of the more electronegative atom. And that atom will take on a permanent negative charge. The one it's bonded to will take on a permanently positive charge. Now, that's just for the bonds. We'll talk about the molecules that made up of all those bonds later. But at this moment, we're just looking at each bond. Is the bond polar or not? Well, typically, it is polar unless it's bonded to the same atom. I told you carbon has chains of thousands or hundreds of thousands of carbons long. Is the bond between the carbon atoms, each individual carbon atom, polar? No, because they have the same electronegativity. So there's no charge separation along that big chain due to the carbon atoms bonded to each other. But if the carbon atoms are bonded to a hydrogen atom, well, what would happen? Well, let's look on our chart. Carbon is 2.5, hydrogen is 2.1, so carbon is more electronegative than hydrogen. So that means that the carbon is going to be a little bit negative, not -1, a little bit negative, and the hydrogen bonded to it is going to be a little bit positive, not +1, but some fraction of an electron's charge, just a little charge separation. That's what we mean by a polar bond, a polar covalent bond. Now, an ionic bond is just the extreme of that. In an ionic bond, say if I had calcium bonded with chlorine, what's going to happen is the calcium is going to actually lose its electron to the chlorine, and the chlorine is going to become a -1. Now, the difference in electronegativity where that occurs is a difference greater than 2. If you've got two atoms bonded together and their electronegativity is greater than 2, that will actually not form a covalent bond at all. It'll just transfer the electrons and it'll form an ionic bond. So that's how we can, ionic bond is just an extreme of polar covalent bond. All right, here's a checkpoint on it. And so let's look at that. Okay, we're ranking electronegativities. And so you can take a look at that. I have to stop the screen share to work with you on it. Let's do that. And now I'm going to set it where I can see and you would have access to it there. So we're going to take gallium and, oops, I didn't. And we're going to take gallium, arsenic, tin, and lead. So gallium, arsenic, tin, and lead. Let's locate them on the periodic chart so we can figure out what the order for the electronegativity should be. Okay, now gallium is in the same family with aluminum and just one below it. So right there is gallium. Arsenic is right there. It's in the same row with gallium, but closer to the end. So when I told you a while ago, which one's more electronegative? The one closest to its end. So, okay. Now, let's see if I got another pen here. Lead is right there at the edge of this little pen. So lead is down below. Now, what's the other one? Antimony. Antimony, I don't have room for all my pens in there, I think, but I'll try. It's right there. So now, I'm looking at gallium, arsenic, tin, and lead. Tin and antimony. Lead and antimony it was. Okay, now I got it. All right, gallium, arsenic, antimony, and lead are the 4 elements. Okay, which one of those is closest to the end? Arsenic, that's right. So arsenic is the larger one. Now, the best way when you're doing this kind of ranking, the 2 extremes are going to be easier to find than the ones that are intermediate. So what I'm going to do when I'm doing this to be test-wise is I'm going to look for the 2 extremes first. I've just said the largest one is arsenic. If this is a multiple choice question, I'm going to mark out all the answers that don't have arsenic as the largest. You know, it could be that's enough, you're done. And maybe the others, all the other answers have arsenic in the wrong place. So I got the answer. I'm sure it's right because it's the easiest comparison to make. And I didn't have to do the work. I can go right on to the next question. Well, what if 2 of the answers have arsenic in the right place? Then the best one to go for would be the smallest. Now, again, remembering what I told you all ago, the one they ranked according to the distance away from the noble gas. So the lowest one would be gallium. So I would put the gallium in as the next one. So I'm going to now look of those that were correct with arsenic in the right place. Is there just one of the rest of the answers and one of those answers that have gallium in the right place? If it is, I'm quitting right now. I'm done, marking my answer and going on. If that's not the case, then I have to put the others in the order that they belonged. And so if I line them up the way I've shown you here, all I'm looking for is the distance, the closest one. The largest one is arsenic. The next is antimony. The next is lead. The least is gallium. And I can get that very simply by looking at the periodic chart. Now, let me warn you. You Google this, I'm betting that's not the correct answer in Google. And Google is probably right. But remember, I'm not asking you for the answer. I'm asking you for the process that will get to the correct answer the quickest possible. And you are not supposed to be using Google when you're on a test. If you are, I'm probably going to pick one that'll make you miss it. Okay? So focus on the principles. That's the easiest thing, and that carries it with you. And then there is one on D2L that you could do, but you can work that out on your own. And then if you have questions about it, email me and I'll respond to you there.
Dr. Pearson, do you mind saying that order again?
I'm sorry?
Do you mind saying that order again? I missed the last one.
The order again? Okay, sure. Oh, let's see. Somehow, okay, I have to go to the checkpoint. Whoops. Nah. Okay, yeah. You see my textbook over here with the periodic chart?
Mm-hmm.
What I've done is I've laid down a pencil for each element. So there's arsenic, there's gallium. This one is supposed to be on antimony, and this one is on lead. Now, to make the comparison, all I've got to do is read the tips of those pencils off from right to left. The one that's closest to the right is going to be the highest. So arsenic is going to be the highest. The next one I come to is antimony. That's going to be next. The next one I come to is going to be lead. And the last one I get to is gallium. So all you're doing is look, if you're doing this on a chart, on a quiz or an exam, what you would do is put that periodic table down, circle each of those elements on that periodic table, and then just read them off. The one that's closest to the right-hand side is the largest, and the one that's furthest from the right-hand side is the smallest. Make those two comparisons first, and then if you have to go to the others, then you can read the others off as well. But it's quickest to do that on a test situation, because as soon as you've got all the other answers eliminated, then you know the answer that remains is the correct one. A good old philosophy from Sherlock Holmes. If you eliminate what's not possible, what's left is what is. All right.
So much.
Okay, very good. Now, the next part that we're going to do involves the VSEPR notation. So I think I would like to maybe we've got plenty of time to do that tomorrow, and also do the quiz. Yeah, I'm pretty sure we do. So we'll do the quiz tomorrow at 7:30. I'll have it open up for you. I will set it for 25 minutes, and you'll finish that quiz in, and then we'll begin our Zoom lecture to finish up 7, and then exam 2 will be Wednesday as on the syllabus, and then I think we'll have the syllabus all lined up pretty well. I am making revisions in what was the labs. I've got the labs all designed now for the rest of the course. I'll put them up typically either the day before or the day of the lab. We'll go over it in here, and I'll put the files up available for you. And so let's it's about 5 to 10. Let's say come back at 10:10, and we'll talk about today's lab, and I'll answer any other quick questions you might have about the quiz for tomorrow. So let's say we're going to be back at 10:10. Okay, there you go. I think you're going to do well on this quiz. I really do. Just looking over it, there's really only 2 difficult problems, and that was the ones with wavelength problems and masses of photons and things like that. And those are difficult problems. They really are. I understand that, but you practice on them really well, and you'll do well on them. Okay, see you in a few minutes. Let's stop the recording.